Thank you, Michael. Can everyone hear this? I guess the mic's on. And welcome to the summer school. I don't even know what edition this is. It's probably in its teens, though, because 13th edition. And this started, I guess, when the Professor Law was the director of the Combustion Energy Frontier Research Center, which is a project with about 12 PIs to solve some of the energy problems in combustion a long time ago. And so I was part of that team, and he founded the summer school as an outreach activity coming from the CEFRC, as it was known. So let's see, I guess today what I'd like to talk about is Michael alluded to that my career has been spent mostly doing high-performance computing, and especially one form of it, which is direct numerical simulation, DNS in short, and where we're solving the full turbulence equations with no closure models, but we do have to have models for the chemical kinetics and for the molecular transport and any other multi-physics that we include in DNS when we try to simulate directly combustion processes. But before I start, so what I'd like to do in this course, it's a short course, and it's more of a survey course to kind of let you know what people are working on now as far as applying exascale computing, and coupled with that, reduced order modeling, deep learning, and machine learning to be able to accelerate DNS and also to provide closures for very difficult, complex combustion situations. And trying to focus it now on decarbonization of applications for generating power and also for aviation. So just to give you a little bit of background about myself, as Michael has said, I've spent my entire career in combustion at Sandia National Laboratories in Livermore, California, where the Combustion Research Facility is located. There's a photo of it here. And the Combustion Research Facility was founded in the early 80s, following on the energy crisis in the 70s, probably way before all you guys were born. And this was as a fallout of the 73 oil crisis and the 79 oil crisis that were spurred on by the Yom Kippur War and then the Iranian Revolution, which triggered a lot of delays and interruptions from the Middle East in terms of exporting oil to Western countries like the US. And so this caused recessions and what they called stagflation and so on. And as a result of that, there was a real need to improve on the performance and efficiency of burning oil in combustion. And so the Combustion Research Facility at Sandia, the CRF as it is known, was established as a result of that. The facilities got a bunch of office and large laboratory scale labs. I think there were 30, at one time there were 36 highly specialized labs where they were doing research on laser-based diagnostics and on engine combustion and computational work. And about 10 years ago, there was a second building you can see in the picture on the left of a computational facility over here, one-story building that housed a cluster for computing that we were performing. And of course, the CRF was established as a collaborative research facility, meaning that people from around the world, visitors and collaborators, students, postdocs, would come and utilize the unique facilities in the laboratories and also their computations in order to conduct combustion research. On the other hand, we also had very strong collaborations with US industries, particularly in the automotive space, through a consortium called US Drive that Sandia had leadership roles in. And so you can see a lot of the companies that were part of that. So it was pretty much soups to nuts for the fundamental combustion science research that was performed at CRF, starting from the very basic chemical physics associated with gas phase kinetics, so chemical dynamics, spectroscopy, looking at theoretical chemistry, so these would be things like ab initio calculations, potential energy surfaces, master equation, and then looking at elementary kinetics, potential energy surfaces, and then flame on up to flame chemistry, so things like flat plate burners, stagnation point flows, to measure species, minor species, major species temperature, soot, various optical diagnostics that were developed as part of this research effort, and then into developing mechanisms, chemical mechanisms that could be coupled in CFD problems. So, and not only detailed models, but also mechanism reduction and uncertainty quantification. From there, there are efforts to look at laminar and turbulent flames, both experimentally as well as computationally. So this is where my efforts have been involved, mostly on the laminar and turbulent flame high-fidelity simulation end of things. And then there have been a series of experimental benchmarks that many of you may know, Rob Barlow and Jonathan Frank, they kind of led the Turbulent Non-Premix Flame Workshop. It's a biannual meeting that happens preceding the Combustion Symposium every other year. And so there's a lot of high-quality experimental data that modelers can use this benchmark data to test their modeling hypotheses. And then on up from these lab-scale flames, we go to actually high-pressure spray flames that are more representative of applied applications like internal combustion engines and gas turbines. And so coupling all of this atomistic to fine continuum all the way up to application science, all the way up to applications that Ford, GE, GM could use to design and optimize designs of engines. This work is done at the CRF. Okay, so what I'd like to do this lecture will have 5 parts. I'm hoping I can get through all 5. First part is kind of an introduction and motivation, and then a little bit about the governing equations that we solve in these first principles DNS calculations, and what it involves to actually perform these calculations at scale on some of the largest supercomputers that the world has. So if you want, unfortunately, turbulence is multi-scale by itself if you want to get to high Reynolds numbers, but when you add in multi-physics like chemical kinetics or sprays or soot, the problem becomes even more expensive. And so you have to do these calculations on these large supercomputers. And supercomputers have evolved from Beowulf clusters, actually the early Crays, vector machines, to the killer micros and the clusters. And then more recently, because of power demands, they've gone to GPU machines and lots of them. So the world's largest machine now sits at the Oak Ridge National Lab that's put up by Department of Energy on their leadership computing facility, and it's got upwards of 50 to 70,000 GPUs, AMD GPUs that have to work together if you want to run a really, really large job. Okay, so that's the first part, and then the second part, second, third, and fourth parts are to give you some exemplars or vignettes of if you could do the DNS, what could you study, and what would you learn from it? And so I'm going to talk about some of the renewable zero carbon fuels today, or biomass-derived fuels. And I'm going to focus mostly on hydrogen combustion, ammonia combustion for power generation. And then I'll focus a little bit, probably tomorrow morning, on aviation and what to do there, because you can't electrify airplanes, because it's just, especially the long haul or the long distance flights. Short ones, you might be able to electrify it or use hydrogen, but an alternative is to use sustainable aviation fuels that are derived from biomass. And so what are some of the complications involved in getting that to work as a drop-in fuel for conventional jet fuels? And then tomorrow, after we get through the 3 vignettes, then tomorrow I'd like to talk a little bit about reduced order modeling, and especially as it pertains to how to speed up these very expensive DNS. So can we accelerate it by using a surrogate DNS, taking advantage of the correlations that we know exist in the dependent variables, especially with the chemistry. So species are not all independent, they're very much coupled. And so you can exploit that knowledge to reduce the cost of the DNS and to vastly accelerate it. So I'd like to talk about a few methods in that direction. And then I'll finish with what our community is doing now as we're moving more and more to relying on machine learning and deep learning kinds of things. And we need training data for which these high-performance computing calculations contribute to that. And there's an effort in our community led by Stanford, Matthias Ehm and his student Chen, on standing up a public repository for training data for combustion called BlastNet. And so I'll finish up tomorrow afternoon with that. So that's kind of an outline of what I'm going to be talking about. So let's start. And by the way, if you feel free to interrupt me and call me Jackie. So the world has been enamored with fire and combustion since a long time ago. And through the evolution of cooking around fires and using it for warmth, to where we had the Industrial Revolution with the steam locomotives, and then eventually the development of automobiles and trucks for shipping. And a lot of this happened, this demand and technology advances happened during the Industrial Revolution, which started around 1760. And then since then, our appetite for energy, for moving goods and for powering electricity, heating our homes, so on, has just gone up and up and up, especially across the world. And so there's a huge demand for energy, but at the same time, and we can see that the energy consumption is coming from various sources. And this is just a Sankey diagram that shows the sources of the different types of energy on the left and the consumption of it on the right. And I just want to call your attention to a couple boxes here. So electricity generation, which comes primarily from natural gas. This is a 2022 Sankey chart. Consumes about 38 quads, 100 quads. Quads of electrical energy. On the other hand, and residential, commercial, industrial use of power, if you sum that up, it's probably about 30–40%. And that comes also a lot of it from natural gas. You can see the blue lines going towards those sectors. I should say that electricity generation, the width of these lines indicates how much of the source, how important that source is. And so it's coming from not only natural gas, but also from nuclear, and it's increasingly coming from solar, and there's a little bit also coming from wind. So it's kind of a mix for electricity generation. On the other hand, transportation, that would be cars, trucks, ships, trains, planes, consumes about 27.5 billion, I think, million or billion quads. I don't know what the units are here. And that looks to be coming from this green line almost exclusively, with a tiny bit coming from biomass, which is the light green line, and that's coming from petroleum. So by and large, in 2022, we're still mostly getting all of our energy from transport from burning conventional fuels like oil and gas, or oil, I should say. So as a result of the Industrial Revolution and our energy needs, modern energy needs, the global mean temperature has continued to rise since the mid-1800s. And in fact, this last year, 2023, was the hottest mean temperature since of, I think, 1.4 degrees Celsius. This is the global mean temperature above the average temperature from the 1850s to 1900s, or the pre-industrial baseline. And this is the first time that the mean temperature has exceeded the pre-industrial baseline. And so under the Paris Agreement, many of the countries have an aspirational goal to try to limit the long-term global warming to no more than 1.5 degrees Celsius. So we're going to have to do a lot of mitigation strategies and introduce sustainable fuels and so on in order to try to meet this objective. This is an older chart that I have where we just see where the greenhouse gases like CO2, methane, nitrous oxide, and other gases are coming from over time. And so from the early 1800s to a little past 2000, I don't have a more recent chart that I could find. The total greenhouse gases was 9 billion metric tons of carbon per year. And by and large, most of it was coming from conventional fuel. So it's coming from burning petroleum, coal, and natural gas. So the blue, green, and red lines accounted for the lion's share of where the greenhouse gases were coming from. There was a little bit coming from cement production and from gas flaring. So this is a more recent chart. It says that the total emissions in 2022 are 6 billion metric tons equivalent. And again, you can see where the greenhouse gases, the sources of greenhouse gases are coming from, again, commercial, residential, industrial sectors, increasing substantially when these indirect emissions are coming from electricity end use are included. This is due to the large amount of electricity use from heating, ventilation, air conditioning, and lighting in buildings, and also at home, at residential places with appliances and plug load. And so for powering, and also for manufacturing and powering industrial machinery. In transportation, as I said, the greenhouse gas emissions are mainly coming from burning fossil fuel for automobiles, trucks, ships, trains, and planes. And consistent with the other graph I just showed you, over 94% of the fuel that's used in transportation today is still petroleum-based, even though there's a push to electrify the passenger fleet. So here's another chart that's quite interesting. Since 1990, you can see that the US greenhouse gas emissions have started to come down a little bit, but just over 3%. And there are fluctuations from year to year, but you can see around 2020, there's this dip in the curve, and that's where COVID-19 hit, and the world pretty much was at a standstill. And so there was the energy, we used a lot less energy there for transportation, and then it has since picked up in the last couple of years. And so overall, it's kind of steady. It's going down a little bit, but not enough. What about looking not historically, but projecting into the future? So the world electricity demand is projected to grow a lot for all different scenarios. Policy or energy studies have, from all these different studies, are projecting what the energy mix demand or sources of energy will be by 2050. And so all of the chart shows that right now in 2022, coal and natural gas, the brown and blue colored ones, are still over 50% of the sources of electricity generation, with the rest being made up of wind, solar, hydrogen, and hydropower nuclear. But what you can see is the trend is that coal and the natural gas will continue to go down in 2050. But what we anticipate in all these different analyses is that wind and solar will become almost half, if not more, of the source of energy generation for electricity. So the green and yellow lines, even under conservative estimates, for example, the IEA, International Energy Agency STEPS program predicts something like more than 50% of it coming from these renewable sources in the next 20, 30 years. Okay, so I'll skip that one. But then we want to also ask the question, well, there are some areas, well, it's possible to electrify automobiles that we drive and some other areas. There are also very what they call hard-to-electrify sectors. And these include things like energy-intensive industrial manufacturing, which requires high-temperature heat, like making steel, high-temperature furnaces. Aviation, as I already mentioned, you can't electrify long-haul planes. It's also hard to electrify large agricultural or mining equipment, tractors and things like that. And for marine shipping, carrying freight across the Atlantic Ocean, for example, it's very difficult, again, there to electrify those marine ships. And lastly, large-scale gas turbines are hard to electrify. And so I think we will still be requiring combustion of liquid fuels or gaseous fuels, but we want to do research to support utilization of these low-carbon liquid fuels like biomass-derived sustainable aviation fuels, like liquefied hydrogen or gaseous hydrogen, and various ammonia blends with hydrogen. As a way to improve, we need more research to try to improve the efficiency while also trying to minimize the emissions of harmful greenhouse gases and particulates. So for example, when you burn ammonia, you produce nitrous oxide, which is a significant greenhouse gas. And in the aviation sector, even though you have less particulate or soot formation, those soot particles that come out of the end of the aircraft serve as nucleation sites for growth of ice crystals, which form contrails, which are another major source of retaining the heat on Earth. So what I'd like to talk about is that in the electricity generation or dispatchable energy to offset intermittencies with wind and solar renewables, there's a lot of potential as is going on now with burning hydrogen and even ammonia, blended ammonia utilization. And so hydrogen can be blended. A lot of the gas turbine companies are already working on blending it with natural gas or with increasing ratios of hydrogen as they understand how to use it. And hydrogen is in this chart, it talks about production, transport, and utilization. So most of the hydrogen produced today is made out of a process called steam methane reforming. The process uses methane as a feedstock, and it produces CO2 as a byproduct, which can be captured and stored using CCS technology. And then there's the whole rainbow of color-coded hydrogen, from blue hydrogen to green hydrogen, depending on how it's produced. That could be an alternative way to get hydrogen from renewable energy through electrolysis. That is creating H2 and splitting water, basically, to form hydrogen. And the problem with hydrogen, then, is you've got to store it, and you've got to transport it to where it's needed. And so the problem with gaseous hydrogen is that the molecule is so small that the energy density based on mass where the gravimetric energy density is very, very low. I'm sorry, very, very high, but the volumetric, the specific density is high, but the volumetric density is quite low. And so you have to liquefy it in order to get the energy out. And to liquefy it requires enormous infrastructure. You need cryogenic tanks that are at minus 253 degrees Celsius in order to keep it cold and liquefy it, or if you compress the gas, you need extremely high pressures. On the other hand, there are also ways to store it using liquid organic hydrides, and or you could store it in forming ammonia from the hydrogen, so combining nitrogen and oxygen to put it back into ammonia. And ammonia doesn't have as much difficulty in storing it or moving it as hydrogen does. So you can liquefy ammonia at just minus 33 degrees Celsius, or it only takes 10 bar or so to store it. And a lot of the infrastructure that we have already for moving fertilizers already exists. So that might be a better way, debatable, to store and transport as an energy carrier the hydrogen. And then once you get it to where you need it, you can add waste heat to it and crack the ammonia to form hydrogen again. And so what are some of the end uses or utilization for the hydrogen? In this chart on the right, you can see that it's being used for fuel cells. It could be used for vehicles. I'm going to talk about its use in power generation. And then for ammonia, there are a lot of companies now, especially in Japan, are looking at ammonia direct combustion in large industrial gas turbines, and also in furnaces as well. So this is a lot of work in Europe done in the Scandinavian countries, where there's a lot of marine shipping companies, for example, at Norwegian Technology University and also at Syntef Energy. This is a kind of a cool chart that compares all of the different fuels out there in terms of their energy density, and the volumetric energy density in terms of millijoules per liter is plotted on the ordinate, whereas the gravimetric energy density, or the specific energy density, is plotted in millijoules per kilogram on the abscissa. And you can see that there's not lithium-ion batteries, this black circle, so it's quite low. Hydrogen, as I said earlier, has huge specific energy, and if you liquefy it, it has comparable volumetric energy density to natural gas and liquid ammonia. But none of these fuels they're still way below our conventional. I wonder why it's not. Okay, green doesn't go on white. It's below the red circle, which contains our conventional fuels like kerosene, diesel, and gasoline. And so there are significant challenges to getting the efficiencies and just managing these fuels. And so this is another chart that shows the trade-offs between hydrogen and ammonia in terms of storage and transport requirements, which I kind of already talked about. Basically, the synthesis and conversion of hydrogen processes are only the beginning and end of a longer and more energy-intensive process for being able to successfully use hydrogen as a store for renewable energy. So in order to actually use it and transport it by either ship, train, or truck in its pure form, as I mentioned already, it has to be either liquefied or compressed, and that requires enormous cooling or very, very high pressures. Okay. And then on top of that, it boils off. So there's energy losses due to evaporation or boiling of the hydrogen, about as much as 0.5% of the total volume per day. And so it's a real challenge to store it. Is there a jackhammer outside this room? So anyway, you get the idea. It's hard to ship or move around. The infrastructure doesn't exist. It is also such a small molecule. It leaks. It's highly flammable. And so ammonia may be an alternative as a storage transport vector for hydrogen as we go forward. I just want to point out a few of the other challenges of hydrogen. As I mentioned already, it's highly reactive. In this chart here, we compare some of the properties of methane, hydrogen, and ammonia in terms of the flame speed, flame temperature. So you can see that whereas methane is about 0.4 meters a second, hydrogen burns at about 3 meters a second, and ammonia burns at even half the speed of methane, so it's barely burning at all, has a very low propagation speed. Flame temperature, again, hydrogen is a hotter flame than either of the other two, and it has extremely broad flammability limits. So if it leaks out, it's highly flammable, it has very, very short ignition delay times, orders of magnitude shorter than for methane, and ammonia just hardly needs assistance even to ignite. So usually if you want to burn it in a marine ship, you have to provide a pilot of some sort or add heat or plasma or crack some ammonia or something. So very different properties. And hydrogen, because of its fast burning rates, 300 centimeters per second, I think this is for stoichiometric hydrogen. It's a real challenge to use in gas turbines because it can flash back, meaning near the injector, it can actually propagate upstream and destroy or damage hardware in the gas turbine. It's also high temperature, high heat release rate, which can couple with the acoustics that are in your engine and create thermoacoustic dynamic problems as well. There are also issues of emissions, and so in addition, as I mentioned earlier, ammonia generates nitrogen-bound emissions through nitrous oxide, N2O, which is another greenhouse gas. So you may be trading one evil for another evil unless you can figure out how to mitigate that problem. Okay, so here I just list the challenges. And so we need to figure out methods that how to optimize transporting hydrogen and its combustion system for safe operation. And the trick here is also you want to offset the intermittency. So in these for electricity generation from the renewables, so you want to be able to have load as well as fuel flexibility in these modern gas turbines so that you can quickly ramp up or ramp down the dispatchable power generation. And right now, companies are working on natural gas in combination with blends with hydrogen and also with syngases, with many of the companies trying to push towards burning 80% hydrogen or even all pure hydrogen. So as I said, fast startups and load shifts are a significant challenge. And I've already gone through the property effects, and so the challenges that I think from experimentation and from high-fidelity simulations can start to address the utilization of some of these lean premixed hydrogen combustors in gas turbines like flame flashback, flame holding and stabilization through injection processes, and then thermoacoustics. So the second part of this first part, I'm going to talk about some of the research paradigms. You probably all know that combustion is got a lot of scales and a lot of complex physics. It's not just pure turbulence, so it's not just incompressible fluid dynamics. Large range, this is just an example of inside of an IC engine, diesel engine, measuring the soot incandescence in a lab scale or in an IC engine. And what you see is the in-cylinder geometry can be centimeters, which is probably 10 centimeters or so, which is probably the smallest device you'll find, on up to furnaces or large gas turbines, which are meters in physical length, extent. On the other hand, to have combustion, you have to molecularly mix atoms and molecules before they'll react. And so you also have to, combustion is driven by fine scales, small scale phenomenon that starts at submicron scales, and where a premix flame is on the order of 0.5 millimeter to 1 millimeter thick. And so looking at the combined interaction of turbulence, turbulent strain, turbulent mixing of the reactants, the fuels, and then the reactions occurring themselves can go from microns on up to meters. Similarly, soot inception and particulate formation starts at nanometer scales. So there's a very, very broad range of length and time scales involved in combustion. There's also chemical complexity, and so while hydrogen can be described by 9 species, methane, natural gas, maybe by 20 species in a reduced mechanism. Typically, chemical complexity is very large, so you have large numbers of species, maybe upwards of several hundreds of species to describe soot formation, soot chemistry and precursor chemistry, for example, and thousands of elementary reactions that have to be transported if you want to do a high-fidelity simulation, along with solving for the turbulence problem. Also, the combustion problem is plagued with multiphysics. Typically for liquid fuels, you have to first worry about injecting a liquid, atomizing the liquid, vaporizing the liquid before and it has to mix with the oxidant before it burns. There's also looking at emissions of particulates like soot, so you're interested in the soot particle size distributions, the number of densities, and how that interacts with thermal radiation, for example, if you have a large enough combustor like a furnace. And all these processes are highly nonlinear. Turbulence is nonlinear. Chemical reactions are nonlinear, highly nonlinear, and they're very tightly coupled. So it becomes a very challenging problem. And so most of my talk today, and my expertise, is in the area of gaseous turbulence chemistry interactions. And so at the most fundamental level, turbulence entrains, advects, and strains a flame. And if you think about it, it creates more surface area for burning to happen. And so through the concept known as stretch, which involves both tangential strain as well as a flame's own self-propagation, coupled with the local geometry of the flame as it gets wrinkled, that mechanism of stretch changes the amount of area that's produced for combustion to occur. So, and then turbulence, on the other hand, through the normal cascade from the largest scales of the device, cascades down to the flame scales, which are small scales in the dissipation range of the spectra. They eventually, the reactants there are molecularly mixed, and these reactions will occur and are enhanced with mixing, usually up to a point. So if you strain it too hard or stretch it too hard, you can get local quenching, localized extinction. And otherwise, especially with fuels like hydrogen that are very robust, they can create heat release, very large amounts of heat release and flow dilatation at these small dissipation scales. A quick example of that is when you blow out birthday candles with your kids. The harder you blow, initially the birthday candles get brighter, but it takes a while sometimes to blow really hard before you can put it out. Same kind of idea happens in a gas turbine combustion chamber. And so heat release, dilatation have feedback on the turbulence intensity through the density and through property changes like through viscosity, function of temperature. And the combustion heat release can also modify the spectral energy transfer. So not all of this notion of forward cascade from the biggest scales all the way down to small scales happens as it does for incompressible non-reacting flows. But there could be generation through large amounts of energy release at the small scales that could have work its way back up spectrally into, it may move around, be generated from the fine scales in addition to the large scales. So it's unclear what the spectral energy transfer properties are at the fine scales, and this has, of course, very large consequences on how you model things like large eddy simulations where those subscales are not resolved, they have to be modeled. So using and picking up incompressible notions and models to model highly combusting, to model combustion may be questionable under certain circumstances. Experiments. So the idea here is that we want to combine experiments, computation, and theory. And as I said in the beginning, experiments are in these lab scale flames and also for looking at ignition problems have been done at both ambient as well as high pressures using advanced laser diagnostics, optical laser diagnostics. There's been a lot of development for measurements such as OH, CH, and various other atomic hydrogen, atomic oxygen. There's people making measurements of those kinds of species and radicals, and also of soot through laser incandescence. And simulations have gotten mature enough in the last 10 years that we can actually now start to couple the results from lab scale experimental flames with high fidelity simulations, including DNS, where all the scales are resolved, and large eddy simulation, where we resolve the scales down to some cutoff point, and then we model the remaining as a subgrid with subgrid scale turbulence and combustion models. So they play a complementary role, and they help through an iterative process control the boundary and initial conditions and define the scalars and the velocity field. And through this iterative loop, it's a lot less expensive and helps speed up the eventual design cycle. More recently, data science, especially theory together with machine learning and AI, are stepping in creating new subgrid scale models for these more complicated scenarios, for interpreting the data, and for identifying reduced manifolds, for closure models, and for accelerating computations. So a few computational considerations. As I said, in combustion and practical devices occurs at very highly turbulent flows with large inertial to viscous forces captured by the Reynolds number, turbulent Reynolds number. So it's typically we have 4 to 6 decades in space and time. So it's multi-scale, it's multi-physics, fluid dynamics, molecular transport kinetics, and multi-phase phenomena all have to be considered. So various sub-processes that are connected. And then if you want to solve this with high fidelity, you have conservation equations that have to be solved in a tightly coupled system, also with very large dimensionality due to the large number of species, maybe upwards of 100 or a couple hundred, that you have to transport. That's n species here, plus the 5 other dependent variables for density, the 3 components of momentum, and for energy. And so performing these high fidelity simulations becomes very, very expensive very fast. A word about the spatial scales that you need to consider when you do these types of calculations. You have to worry about the smallest turbulence scales, the Kolmogorov length scales, where energy is cascaded down to the fine scales where it dissipates through viscous effects. And so eta here is the mean Kolmogorov scale, and it's proportional to the largest integral length scale, the ratio of the largest integral length scale to the turbulent Reynolds number raised to the 3/4 power. At the same time, if you want to look at the dissipation of scalar variance, which you have to worry about in combustion, in addition to the turbulence dissipation, you have to resolve the Batchelor length scales. Thankfully, most gaseous fuels have Schmidt numbers, viscosity over mass diffusivity. That ratio is of order unity. In a liquid, that's more like of order 1,000. And so thankfully, the resolution requirements given by the Batchelor scale, lambda to beta here, are quite similar between the Kolmogorov, the turbulence scales and the reactive scalar scales, because Schmidt number here is going to be of order 1 for most gaseous fuels. And then the other length scale that we have to worry about resolving is the flame itself, or the ignition front itself, and that can be really thin. So depending on what regime of combustion you're in, if it's burning as a thin wrinkled sheet, like in a flamelet regime, or if it's totally stirred and mixed by intense turbulence, the length scales can be quite small. They can be smaller than even the Kolmogorov length scale. And so typically, we can say that flames can be 10 to 20 times thinner if they're burning in the so-called flamelet regime than the Kolmogorov scale, which also imposes significant resolution requirements. And so the upshot of this is that for non-reacting turbulence, if you look at the energy cascade, log of the energy plotted here versus log of the wave number, we have the energy containing length scales at 1/L, goes through an inertial range where the fall off is k to the minus 5/3, and then it has an exponential decay down to the place where viscous dissipation dissipates all that energy. And so if you look at the range of scales from the integral scale down to the Kolmogorov scale, eta, then the number of grid points that are required to resolve that goes as that ratio to the cubed power, because it's usually 3 dimensions, so cubed. And then the range from just turbulence scaling, the range of scales here between the biggest and smallest scale goes as Reynolds number to the 3/4 in one direction. In 3 direction, it goes as Reynolds number to the 9/4. So that's a lot of grid points if you want to resolve high Reynolds number turbulence. It gets worse when you want to also resolve combustion. For turbulent combustion, the flame thickness, as I said, can be smaller than the Kolmogorov scale. And so the number of grid points scales as Reynolds number to the 9/4 for the turbulence, and then you have this ratio that's multiplied by it, that is the ratio of the Kolmogorov to the flame thickness cubed. And so that's a very, very large number. And on top of that, you have linear scaling with the number of species that you're going to transport. That can be of the order of 10 to maybe order 100. And so you can quickly see that the cost gets very, very high. Same thing goes if you want to have temporal resolution. In a compressible code, such as S3D, the one I have, you have to resolve sound waves in an explicit method. And so you have to solve for the acoustic CFL, where the time step is determined by the ratio of the grid size and to the sound speed, A. On the other hand, you also have, this one doesn't work very well. On the other hand, you also have to, there it is, solve for the advection CFL, the Carrot-Louis-Friedrichs criterion for a given numerical scheme. And there, the time step, delta t, is proportional, again, to the size of your mesh divided by the convective velocity. And so the ratio of the acoustic time step to the advective time step is simply your Mach number, the ratio of u divided by sound speed A. On top of that, you have to resolve your flame timescales or ignition chemical timescales. And so flame timescales typically scale with the thickness of the flame divided by the laminar burning velocity in a premix flame. Or alternatively, you can define a chemical time scale based on the maximum reaction rate or maximum species creation rate, production rate, inverse of those two quantities, or based on the eigenvalues of a reaction rate Jacobian. And so chemical time scales usually limits our time step in our calculations. And by design, we try to make our chemical time scales somewhat comparable to our advective CFL restrictions too, so that they're not too disparate. Okay, and so even with all the supercomputers, multi-scale modeling of these processes oftentimes requires understanding what's going on at the quantum atomistic scales, on up through molecular dynamics, kinetic Monte Carlo at the mesoscale, and then on up to fine continuum, DNS. And then eventually, if you want to look at predictions and design of actual devices, you're probably talking about large eddy simulations and Reynolds average simulations. And so this information has to flow a lot of times back and forth through all of these scales. So what I've been doing is using exascale computing power to perform DNS at the continuum scales. Maybe now with 10 to the 18 floating point operation per second, you can resolve a moving window of about 4 to 6 decades of scales. Place your window anywhere you want along there, and then you try to develop parameterizations that will help upscale that information to coarse-grained CFD calculations. So now I'm going to focus on some of the DNS and LES, RANS ideas. And so with RANS, Reynolds average, Navier-Stokes, we don't try to resolve any of the scales. And so if you look at the kinetic energy spectrum here versus the wave numbers, you can see that all of the scales are modeled in a RANS simulation. On the other hand, in DNS, we resolve all of the ranges of scales. And then in LES, which is kind of in between, the energy-containing scales are resolved. The energy-containing scales are resolved through here, through somewhere in the inertial range, and then you still have to model the subgrid scale physics that are beneath the size of your grid. And below here is just a picture that kind of depicts this concept of filtering and averaging, where the DNS of a turbulent premixed Bunsen flame heat release rate is shown on the left. If you filter the DNS maybe 10 times or 20 times from the grid size, you get this picture in the second column. If you perform LES with the subgrid closure, you get this little bit more smeared image, but still captures all the large-scale structure. And then if you average in time through the RANS approach, this is the kind of information that you can get. So a lot of that fine structure is lost and encapsulated only in the model. But I want to say that DNS is not free of modeling. It still needs chemical and molecular transport models. And so in DNS, I'll talk about the compressible formulation today. We solve the governing equations for reacting flow in conservative form, where we solve for equations 1 through 4, which are the continuity equation, the momentum equation, the total energy equation for E naught, and then the species continuity equations for each of the species mass fractions y sub I. Grad beta here is the gradient operator in these equations operating in different directions, beta, and yi in this expression in equation 4 is the mass fraction for species I. Capital W sub I is the molecular weight of a given species I. Tau beta sub alpha is the stress tensor. And then if you have any body forces on species I acting in a given direction, those are represented by F of alpha sub I. Q sub beta in the energy equation is the heat flux vector. And capital V of sub beta J is the species mass diffusion velocity. And then omega dot I here is the molar production rate of species I. E naught is the specific total energy. So this is the kinetic energy plus the internal energy. And if you want details of this, they're provided in this reference below. So in our DNS, we only solve the NS, total number of species, minus 1. So we use the inert gas nitrogen as the bath gas, which we don't solve for, because we enforce the constraint that the sum of all of the species has got to equal unity in order to satisfy continuity, conservation of mass. And so we use this constraint number 6 here, to back out the inert gas, such as nitrogen. We assume that we have an ideal gas mixture, so the equation of state is just that the pressure is proportional to density times the real gas constant, temperature, divided by the mixture molecular weight, which is provided by this expression down here. The sum of the species mole fractions weighted by their species molecular weights. And then we can relate the mass fraction y sub I to the mole fractions through the ratio of the species molecular weights to the mixture molecular weight. A couple other relevant thermodynamic quantities are listed here that between enthalpy and temperature. So for the species, some of the species enthalpies multiplied by the mass fraction of that species enthalpy gives you the total enthalpy. And the enthalpies are given in terms of the sensible enthalpy, this integral of the specific heat of a given species at constant pressure integrated over temperature, sensible enthalpy, and then the enthalpy formation is denoted here by HI naught of a given species at a temperature T naught. CP and CB in this expression down here are simply the isobaric and the isochoric heat capacity, CP and CB, respectively, and this integral, CPI dt, is, as I mentioned before, is a sensible component of enthalpy. So these are some of the constitutive relations. We have relations for the stress tensor, tau beta alpha, which, because of variable density, they're both terms here. The velocity gradients and also the divergence of the velocity here are important for reacting flows. We also solve, we need a model for the species diffusion velocities, V alpha I, and also for the heat flux vector, Q sub alpha, that appear in the momentum, species continuity, and energy equations. Mu here is the mixture viscosity, K is the bulk viscosity, and Dij here in the species diffusion velocity is the multi-component diffusion coefficient. D sub T is the thermal diffusion coefficient for species I. Lambda through the Fourier law is the thermal conductivity, and J alpha I here is the species velocity diffusive flux, where the driving force for species I in a given direction alpha is denoted by D sub alpha of I, as given by this expression in equation 13. The driving force vector here involves thermodynamic forces generated by gradients in concentration. That's this first term on the right-hand side of equation 13. Also gradients in pressure, called barodiffusion, and then any other body force terms, such as the gravitational field in the third term. Typically, we neglect term 3, and a lot of times we also neglect barodiffusion. And so in the following, we'll look at the fluxes that appear in these constitutive relations in a little bit more detail. So all the diagonal components of the multi-component diffusion coefficient matrix DII, we assume to be identically 0, and all the diffusive, R0, and the diffusive fluxes and driving forces for all species have to sum to 0, as expressed in equation 15. And then if we assume the species diffusion velocities take on a Fickian form, or mixture average diffusion coefficients. We can write them in terms of the binary diffusion coefficients, Dij, and the mixture composition is given here, and the mixture composition. And so this would be the mixture averaged diffusion coefficients. The binary coefficient matrix here, Dij is equal to Dji, it's symmetric, and the diagonal terms then vanish. We also neglect, as I said, barrel diffusion and any body forces. And so if we neglect the Soré effect, then the species diffusion velocity reduces to this much simpler form, which is this mixture diffusion coefficient divided by the species mole fractions times the gradient of the species mole fractions. And so finally, we can express the species diffusion velocities in this form given by this equation 19. And then we also have neglected the Dufour effect in the premixed or non-premixed flames, and occasionally we retain the thermal diffusion or the Soré effect for premixed flames. The heat flux vector is comprised of three components representing diffusion of heat due to temperature gradients, and the diffusion of heat due to mass diffusion and Dufour effect. Again, here, in most combinations, heat flux vector retains only the heat conduction term plus the flux that's transported by the species diffusion. We usually neglect the Dufour effect. And so if we take these governing equations then and we code them up, we can solve for the compressible reacting Navier-Stokes total energy species continuity equations and discretize them on our grid using higher order finite difference methods. So typically in our codes we use an 8th order centered finite difference method, and we impose a 10th order filter to basically de-alias the solution. As I said before, we treat detailed reaction kinetics and molecular transport models. And then we have Lagrangian particle tracking methods for massless tracer particles. We also have a dilute spray model that treats the spray as parcels of droplets in a point source manner. And then we also have soot models using hybrid method of moments that was developed here by Michael Mueller. We have also added, for dealing with very, very compressible flows like shocks and detonations, we've added a higher order shock capturing method called Wino 7 that allows us to capture these high discontinuous reacting fronts. And more recently, we've added a 2-temperature model, so multi-temperature model for non-equilibrium flows and flames, including not only the transrotational temperature that you would, but also a vibrational temperature that would be out of equilibrium with your transrotational temperature that would relax at a different rate. We've included various in situ analytics and visualization capabilities. When you're generating terabytes of data on the fly, you can't afford to store all of it. Computer centers have to allocate their budget between memory, processors, and storage. And so we're forced to do a lot of our analysis in situ as the run is going on. And so one of the challenges is how to orchestrate not only the forward simulation, but how do you couple that with on-the-fly analysis and volume and particle visualization. In this code that I developed at Sandia S3D, we've also started to include geometry effects so that we're not just dealing with the box or simple geometry. So we use immersed boundary methods to treat geometry, and also a multi-block approach. So you can imagine a bunch of Lego blocks that you piece together with internal boundaries to generate some form of geometry. One message I have is that certainly we did not do this all alone. We have been very, very welcoming of collaboration with computer scientists and with applied mathematicians. We couldn't have done this alone. And this code, for example, has been refactored for various architectures over the last 20 years, from using MPI when it was all CPUs and OpenMP, to now when we have heterogeneous architectures with GPUs and CPUs and whatnot. We use the help from our computer science friends and have engaged in programming for these large machines using unconventional programming models. For example, a dynamic task-based programming model called Legion developed at Stanford. So let me just give you a quick glimpse of some of the numerical methods that are in the code. As I said, it's a finite difference solver, uses a regular Cartesian mesh. It has an explicit eighth order central difference. If you want to learn more about these methods, I'm providing the references here. Generally, this code is an explicit method, so it has four substages, six substages to make it a fourth order method, accurate method. And then, as I said, we use a 10th order filter that's matched with the 8th order stencil in order to remove any spurious numerical noise that accumulates at small wavelengths. And I've already discussed the selection of the spatial and temporal resolutions that is required in order to faithfully resolve all of the relevant spatial temporal scales for the flow, the thermochemical flames and ignition, and also for acoustic time scales. So we resolve all of those scales in this compressible reacting flow. But just a word on boundary conditions, because that can be a lecture in and of itself. We use the Navier-Stokes characteristic boundary condition method for treating inflow, outflow, as well as permeable wall boundary conditions. We also, in some instances, assume periodic boundaries in certain directions, and walls can be isothermal, adiabatic, or they can be permeable so that you can transfer energy mass across the wall. This is a chart that I have shown many times. So it's developed by Tin-Fung Liu and Professor Law here. It gives you a sobering picture of how large chemical mechanisms can be. So plotted here on the abscissa is the number of species K, and on the ordinate on a log, or this is on a log-log scale, by the way, is the number of elementary reaction steps. So hydrogen is down here at the origin. Also, the symbols here are color-coded based on periods of time. And so before 2000 is in blue, and since 2010 is in these starred symbols. And you can clearly see that as you go to more complex fuels, large hydrocarbon fuels, biodiesels, you're way out here at thousands of species and 5,000, 10,000s of reactions. More common fuels that we study, like methane, CH4, isooctane as a surrogate for gasoline, are somewhere in the order of hundreds of species, and likewise number of reactions. Interestingly enough, if you look at the dotted line here, it shows that the number of species, the number of elementary reaction steps scales linearly with the number of species that you transport, where that proportionality constant is about 5. We've had the good fortune, again, collaboration and partnership with people that understand chemical mechanisms. So Tin-Fung Liu and I and Professor Law have collaborated since the early 2000s on developing procedures to reduce these detailed chemical models and remove chemical stiffness, so disparate chemical timescales that you have to integrate over. So starting with a very detailed model for ethylene with 70 species and for heptane with 500 species. This is what chemists start with as they compile all of the measurement data from shock tubes and theory and so on. Then we apply dimension reduction with directed relational graphs, which identifies unimportant reactions and species to reduce that down to a skeletal mechanism that might contain, maybe half to a quarter of the number of species that were present in the detailed model. Then through further timescale reduction, assuming quasi-steady state assumption or partial equilibrium assumption, then we get reduced models that may be of the order of 20 species for ethylene and 60 species for N-heptane. Then if we look at diffusive species bundling, you can, because evaluation of the transport coefficients is also very expensive. And so Chen has identified a minimal set of diffusive species and grouped them together. And then lastly, he does on-the-fly stiffness removal and results in mechanisms that we can actually ingest in our CFD calculations with about 20 species for ethylene, on the order of 60 species for N-heptane. So this is a very important step. So we do our chemical mechanism reduction a priori up front, and then we can still use an explicit integrator. For data parallelization, as I said, we have a fixed mesh, and we have a trivial, S3D is parallelized using a 3D domain decomposition and MPI communication. Each of the MPI processes, as you can see in the box on the upper right, is in charge of one piece of the three-dimensional domain. And then all of the MPI processes here have the same number of grid points and the same computational load. And so the inter-process communication is only between the nearest neighbors in this three-dimensional topology. The messages for a typical problem are approximately about 80 kilobytes. We have padded each domain with the ghost zone around it so that we can pass stencil information to construct convective and diffusive terms from the finite difference method. And then the ghost zone at these processor boundaries is communicated using non-blocking MPI sends and receives among all the nearest neighbors in this 3D processor arrangement. And all-to-all communications we try to minimize that because that's costly computationally, and then we only do that when we have to monitor for the adaptive time step changes, or for error monitoring, or for something else. But we don't do that very frequently, and of course you have to synchronize ahead of writing out data in I/O. This plot on the bottom right shows that S3D gets excellent parallel performance. This is kind of a little bit older chart from back in 2009 when the machine was called Jaguar at OLCF, Oak Ridge Leadership Class Machine. And what's plotted here is the throughput on the ordinate, the cost per grid point per time step. That's commonly known as the grind time. Question? This is all structured meshes. Yeah, sorry, I didn't say that. We're not dealing with unstructured meshes. I'm not dealing with that. This is a single structured mesh, yes. Now, in later I'll talk about another code technology, which is an adaptive mesh refinement. It's also block structured, but it's block structured, and there's a nested hierarchy there of meshes. Okay, so what I'm showing here is the throughput versus the number of processors in thousands on abscissa, and a flat line is ideal scaling. So this would be perfect performance. And typically, turbulence problems weak scale, meaning that you have this, for a fixed problem size, you just grow the problem by giving the same amount of compute load to each processor. So we don't usually operate in the strong scaling limit. And we get nearly a flat line on the different processors. So we got pretty close to ideal weak scaling on Jaguar back then. This is just another idea that shows the decomposition onto, for example, of a flame onto 4 different processors, 1, 2, 3, 4. And it gives, the picture on the left gives you the notion of bulk synchrony. So processor 1 finishes and it has to wait on processor 2 or other processors to complete their work before it communicates and exchanges information. So interprocessor communication, as I said before, is only between the nearest neighbors. Bulk synchronous codes are slow because the longest time kind of sets the stage for all the other processors. So if you could find a way to be asynchronous, where you could, one processor could complete its workload and march ahead, as long as there was no interdependence of what it was the intermediate solution that it was generating by other processors, then you can save a lot. So this is just a description of the main loop of the DNS solver for an explicit reacting flow solver. We basically compute rates of change of the conserved quantities N. This is the five dependent variables plus the species, NS species minus 1 at every single grid point. And then we just simply we basically just have, it's very simple. We have a advance in time, d by dt, of the dependent vector, which was the N conserved quantities, equals the right-hand side. The right-hand side here is arranged in terms of the advection, the diffusion, the fluxes of heat, diffusive fluxes of heat, species, and then source term for the chemical reaction or whatever other sources you want to include. Sum of all the terms that contribute to the time derivative, as I said, we just call that the right-hand side, RHS. It's integrated explicitly in time using fourth order 6-stage Runge-Kutta method. And the right-hand side, these terms here are constructed. They contain a bunch of terms that are added together algebraically that are functions of the dependent variable vector, Q sub k. And these are variables derived from Q sub k. The advection and diffusion operators in RHS, these two terms require spatial finite differencing. And therefore, these terms require communication with the nearest neighbor ghost zones using MPI or CUDA now on GPUs. The source terms and other thermodynamic quantities, the reaction source term or properties, are point-wise physics. So they don't have any spatial dependencies. So as the last bullet says, the thermodynamic, chemical, and molecular transport properties are all point-wise functions of the solution vector. For chemistry, we are coupled with the solver Chemkin or with Chantera. And we have to call, if any of you guys are familiar with Chemkin, you have to call a routine called CK-WIP, or in our code, we call it get rates. Chemical reactions are computed using an Arrhenius model in its simplest form, A plus B goes to C plus D. The forward reaction rate depends on a pre-exponential multiplier multiplied by the concentrations of the reactants times the temperature raised to a power A, and then it has this nasty transcendental function, the exponential, raised to the ratio of the activation energy to the temperature. So this is highly nonlinear and highly expensive to evaluate. Then we get the reverse reaction rates, so that gets us the forward reaction rate. The reverse reaction rates are computed from the equilibrium constant. And then when we deal with pressure effects, we also have to consider three-body efficiencies. So collisions of three atoms or molecules and their collision efficiency, so there are pressure correction terms that have to be added. And then the source term for a given species then is the sum of the rates of all the reactions in which that species participates. Normally that's not that many, maybe a handful, but so therefore there's room for exploitation for those correlations. The kernel for chemistry uses exponentials and logs heavily, and just to give you an idea, hydrogen with 9 species, 15 reactions compared with primary reference fuel for gasoline that has 171 species and 861 reactions. And the PRF is very, very stiff numerically, whereas some of the smaller models are less stiff. And so we've looked at a whole range of different mechanisms. So high-performance computing. Along about the time of 2010 or so, we realized that to go climb up to larger computers, so this concept of Moore's Law, where people were increasing the number of transistors that they could pack onto microprocessors and doubling it about once every few years. But the problem is that power was a limitation. You didn't want to build a supercomputer that required 100 megawatts of power to run it, because you'd have to park your computer next to Hoover Dam or something like that. So the major computing vendors and government wanted to keep that power footprint down to more like 10 to 20 megawatts, or 6 megawatts as it was back then. And so the primary design constraint for HPC systems was power. And so computing doesn't cost power a lot of energy, not nearly as much as moving data or copying data around on a processor costs a lot more power, energy. And so we wanted to figure out how to write our codes in a way that minimizes data motion on the machine. There are other challenges that in order to get that parallelism and the speed up, we would have to have exponential growth of parallelism within chips, so large concurrencies. And then the notion of locality, as I already said, is how to reason about data locality and possibly topology. So it's not enough just to stick your code on a machine and just let it go, because you're going to get it's going to cost a lot. Usually power translates also into CPU time, so you have very expensive calculations. And then it realized that GPUs are low power compared to CPUs, and so machines became more and more heterogeneous now, with most large supercomputers operating mostly on GPUs. And so there's a lot of performance non-uniformities when you go from CPUs to GPUs, or a blend of those processors, or even tensor processing units for data learning, all on the same machine. So you need to understand how to orchestrate your calculations so that you don't sit there and wait for one to finish and the next to start. So the trick then is to express data locality and independence, massive parallelism, minimize data movement, reduce bulk synchrony or synchronization. You want to be completely asynchronous if you can. And then because the machines are so complicated and large, you want to detect and address faults so you can store your data or in a graceful way before it crashes. So around 2011, the US Department of Energy started an Exascale computing initiative, where they asked 3 projects, combustion, nuclear energy, and climate folks, to team up with computer scientists, applied mathematicians, and domain scientists like myself to start to co-design what an exascale machine might look like, what algorithms we would use on it, and how could you iterate and get the best algorithm with the best hardware within certain energy and cost budget. Along the time of 2016, the ECI, the initiative, became an actual exascale computing project, also funded by DOE, and that was a 7-year project that just finished in December. And this brought together not only the development of applications. There were 24 applications that were developed, including in areas of national security, energy, which is where combustion fits, climate, earth systems, materials. There's also some health applications from NIH. And it delivered also a very capable software stack that would be able to support all of these applications. And co-design centers where there were cross-cuts between machine learning, mesh refinement, PDE discretizations, online data analytics, and so on, that a lot of applications could draw from. And lastly, it provided hardware and integration, knowledge and research to various high-performance computing vendors in the US. So the Crays, AMD, NVIDIA, Intel, those kinds of companies, and that would focus on the development of an exascale node, the huge interconnect that connects all these processors, and system integration. So one of the projects that was formed as Combustion under the Exascale Computing Project, or ECP as it's known. And here in this project, we developed block-structured AMR, adaptive mesh refinement codes. The compressible code is called PELI-C, and PELI-LM then is our low-mach code. We've added multi-physics capabilities to this code, including spray soot radiation. We have a real gas equation of state using Swab-Redlich-Kwon formulation. And it also includes embedded boundaries and cut cells to treat complex geometries. And so DNS from S3D, which was simple block or multiple blocks, kind of primitive geometry, to AMR plus geometry, got us to go from simple canonical flows that we could simulate on up to actual application relevant geometries, still at reduced scale because, but much more relevant. We also teamed with folks at Argonne National Laboratories, where they have a very strong chemistry group, and they developed tools, theoretical tools that would allow us to get automated mechanism generation. This, by the way, was a collaboration among a whole bunch, or 3 or 4 national labs, plus collaborations with several universities, including Bill Green at MIT and Tim and Liu at University of Connecticut on the chemistry side. And so with this capability, we thought we could start to treat things like IC engine combustion and gas turbine combustion and even supersonic flows. So this is just a movie in the upper right corner showing reactivity-controlled compression ignition engine, where we inject endodecane, 4 jets inside of a piston engine into that had previously contained methane in it. So it's like a dual injection, multi-injection compression ignition problem. And we were interested in watching the ignition process of the pilot, and then what intermediate species, cool flame species, were left when the main endodecane was injected subsequently. So played around with things like the duration of the pilot injection, the time lag between the primary and pilot injection, and then mixing ignition kind of phenomenon. We're able to look at very fine details with AMR at high pressure. So you can see in this picture the temperature, heat release rate, hydroxyl radical, and formaldehyde intermediate species resolved down to 8 microns in resolution when we're looking at a piston cylinder that's 2.5 centimeters across. So that's a lot of scales that's being resolved using this block-structured AMR code. And this again shows the weak scaling of the low-mach code on Frontier, which is the world's fastest supercomputer at the moment. And you can see, again, the excellent parallel efficiency broken up into the components of the different physics that's being solved. But you can see that it scales well on up to several thousand nodes, almost up to 3/4 of Frontier, which has 8,000, 9,000 nodes in total. So what have we done with this Exascale code? We've started now to look at performing DNS of multi-injection ignition for diverse fuels. Some of these are alternative fuels like alcohol to jet for unmanned aerial systems like drones for the military. We've started to look at flame stabilization under fuel lean operation or close to lean blow-off conditions with spray combustion and using sustainable aviation fuels, which have very different ignition and physical characteristics from conventional jet fuels. We've also dabbled in, not dabbled, but we're working on hypersonics, and so we're looking at predictions of planar and oblique detonations and also flame holding in a scramjet ignition type problem with this capability. And we've been using this code also to look at dispatchable power generation with hydrogen and hydrogen blends with ammonia in rich quench lean kind of combustor technologies. So the multi-physics insights from these complex reacting flows and is provided by these tools, and also the data that we produce from these simulations can help with reduced order modeling. The second code that developed here is S3D, which is, as I already talked about, I guess I can just skip this one because I've already described this code. But I want to say one thing about S3D, because it was kind of an experimental code for computer scientists that were looking at programming models and runtime systems that are important to get performance out of your code. And so we recognize that to get that we would need a programming environment that would effectively map our algorithms, our functions and tasks to the hardware at hand. And the supercomputers refresh, new hardware comes on board usually every couple of years, 3 to 4 years. So you don't want to hand code something, hand bake it in, and then have to start over again in 3 years. And so the computer scientists at Stanford, led by Alex Aiken and his team, simplified the programming model to express locality and independence. So using their runtime system, it could automatically discover the parallelism and hide latencies by interleaving various tasks that don't depend on one another. And that is dynamic and depends, of course, on the particular data, because different data behave in different ways. And so we simplified the programming of extensible workflows so we can code things sequentially in the languages that we recognize, like C++ and Fortran, and then let the Legion system make the code performance portable for other architectures by having a separate mapping utility that maps this code to different architectures and hardware. And we've applied this to block structure PDEs, analytics, UQ for performance, and so on. So just to drive this point home, I think it's our job to write functionally correct application codes because we're the physics or engineering experts. And then usually we have to figure out how to write these codes for certain machine architectures, so mapping it to a target machine. We have to be able to extract parallelism and manage all the data transfers. We have to schedule tasks so that we can hide latencies, and then do this all over again because a lot of this behavior depends on your data, right? How complex, how stiff, how large, how many species. So it's data dependent, unfortunately. So a lot of people give up because it's too complicated for one person to wrap around their head. That's what you get. So rather than doing it that way, we should write functionally, we should have a compiler and runtime that understand the data. And so the idea here would be that it's our responsibility to write functionally correct application code and to figure out how to map it onto a target machine. But it's the computer scientist's problem to do the rest of it that's shown in green. And so I think the idea of separation of concerns is really important here because you want to take advantage of what the experts know well in computer science, whereas we know the physics well and how to encapsulate that in software. So we wrote S3D in this Legion data-centric programming model, and it's a dynamic task-based model that automates a lot of the aspects of getting high performance, such as task and data level parallelism. It also does performance optimization by scheduling, automating where your tasks are computed and how data is moved around. As I said before, data motion costs a lot of flops and energy. So I don't want to figure that out. I want a runtime to do that for me. And then it separates the specification of the tasks and the data from its instantiation on the actual hardware, and it uses a mapping utility on a given machine to get performance portability. So if I run on Oak Ridge's Frontier machine, which has got a bunch of AMD GPUs, I want to have that be performance portable to another machine that is running with NVIDIA GPUs or with Intel GPUs. I do not want to rewrite my code every 3 years. And so this proof is in the pudding. So if you look at the the weak scaling plot again on the right. What I'm showing here is the throughput again, grind time per node, and number of nodes at this time on Titan, I think, was up to 13,000 nodes, 14,000 nodes. The weak scaling for the Legion S3D code is shown by the blue symbols, and the red symbol shows the MPI Fortran version of the S3D code. So you can see that at low node count, we actually got about a 3x speed up by using Legion instead of MPI Fortran. But we got even a better speed up of 7x when we went to the full extent of the machine. And that's because Legion was able to hide the latencies of communicating across a large network where the larger distances had more latencies. And so I would not have been able to do that by a handwritten code. And to show the significance of this, we combined in situ analytics. In this case, it was chemical explosive mode analysis developed by Tin-Fung Liu called CEMA, which is basically an eigenvalue solve on the reaction rate Jacobian. And we use the knowledge of the timescales, the eigenvalues that are positive are explosive, and the ones that are negative are not. And convolving that with mixing rates or dissipation rates, we could determine the mode of combustion that is occurring. And so to run CEMA at each time step as a diagnostic to steer, for example here, mesh refinement, would take longer than a single explicit Rajikutta step. And we have six substages per time step. And dividing this algorithm across multiple RK substages and then interleaving it with other computations so that they don't impact other critical operations would have been ridiculously hard to schedule manually. But with this Legion runtime and programming system, we were able to do asynchronous task execution, scheduling CEMA analytics on the CPU resources where some of the computation was actually running on the GPUs. And the interoperation between Fortran CEMA with the Legion code took the CS guys only a day to implement. It would have taken us months to handwrite this code. And so when we compared the execution overhead of the in situ analytics, we see here we tested two different machines, PISDAINT at ETH in Zurich at that time, and Titan at OLCF, Oak Ridge National Labs. Without the analytics, CEMA is shown in red, and with this eigenanalysis is shown in blue. And you can see that it took a little over a second to compute the CEMA on Titan, half a second on PISDAINT, but we essentially got it for free. Cost is about the same on PISDAINT with Legion, and only an 84% cost savings on Titan. So the runtime system analyzes and allows mapping of time-varying dynamic application workloads, infrequent changing and data-dependent analysis in viz operations. So the lessons we learned from this is that it's a good advice to collaborate with multiple disciplines. It shows the power here of data-centric, task-based models. And code is just generally easier to modify and maintain. Ports are just new mappings, easier to tune for performance. And then let the runtime figure out all the dependencies and scheduling. And productivity requires this higher level abstraction layer for us scientists and engineers to write in and leave the rest to the CS guys. So we've been collaborating with them for now 10 years as we move from one level of supercomputing to the next. And this is kind of just a plot showing the Moore's law as it applies to DNS of turbulent combustion. And what I've plotted here on a semi-log plot is the computational problem size or computational intensity of these DNS calculations dating all the way back to 1995 or 1996 on up through over 2 decades of computing. And you can see that the exponential growth in HPC, we're able to keep up with that with our simulations, largely through these co-design efforts with CS guys. And back then, in 1995, when I started this business, we were working on 2-dimensional domains with one-step, global step reaction mechanisms, no turbulence because it's only 2D, or 3D turbulence with infinitely fast chemistry. And nowadays, we can actually simulate laboratory scale flames, either free jets or in simple geometries, or with this AMR code with geometry, we can actually simulate more complex aero-engine combustors with multi-physics. We've simulated a bunch of these DNS cases over the years, and we've archived them now on HPSS at various supercomputing centers, but there's a movement afoot in our community led by Matthias Ehm at Stanford to create, and Weitong Chung, to create a community database called BlastNet, which is built on top of Kaggle, and it's accessible on GitHub. And so I think there's been like 20, 30 some DNS data sets from around the world that have been contributed to BlastNet. And these data sets have been curated, and metadata about them is saved so that researchers can use them for model validation and training data for deep learning. So I just want to give you a little heads up for what's to follow. So I think we're in an era now where high-performance computing, first principles DNS, LES, coupled with data science is really taking over. So we're using data science to come up with reduced order physical models and surrogate models for DNS to speed things up. We're including in situ visualization, feature detection tracking, statistical aggregation and visualizations, more complicated workflows. For example, here on the right, we've been working with CS guys to develop level set restricted Voronoi tessellation to capture and segment complicated turbulent flame surfaces, for example, with cellular instability. This is true across not just combustion, but across a whole wide range of science disciplines. So it's where the future's headed. So I want to take a break now for about 5 minutes so that before we come back and talk about hydrogen and ammonia combustion.